I'm Keith Vertanen from Michigan Tech, and this is work with my students, Crystal, Dylan, Jacob, and my colleague, Parola, who's at University of Cambridge. So here's the problem we're working on. So it's a familiar one. You're entering text with an auto-correcting virtual keyboard. So maybe this is, kind of the typical scenario. So you're entering text on something like a smartphone. In this study, we're going to look at sort of making it a little harder. So we're going to enter text on a full QWERTY keyboard that's on a smartwatch. But really, we're kind of interested in this problem in general. So maybe you're doing entry mid-air in VR or AR. Maybe you're entering text without visual feedback. So you're trying to do it eyes-free, maybe due to a situational impairment, maybe due to an actual visual impairment. Or maybe you're entering text on a surface that doesn't have a visual display. And so the research question is, how much input should you provide to a probabilistic autocorrection algorithm when you're typing text on a virtual keyboard? So you can enter text a word at a time, you could enter text several words at a time, or maybe you can enter an entire sentence before you ask for autocorrection. And so that's essentially the research question we looked at in this paper. So to do this, we built a system for a smartwatch. So we built it on the Sony Smartwatch 3. And we've got a full virtual, full QWERTY keyboard. So we have all the letters from A through Z, plus apostrophe. There's no space bar on our keyboard. So I'm going to show you a video in a second. But basically, instead of hitting a space bar to request the autocorrection or the decoding, you're going to swipe to the right. So that was sort of for screen real estate reasons, as well as sort of the right swipe gesture is a nice deterministic, easy to recognize thing. So it kind of provides a nice, fixed spot so people always know they're going to get recognition when they swipe to the right. So whenever their finger's down, you can see in this screenshot here, you can touch down and move your finger around, and it will show you the letter you're currently over in a large font in the text area. So this allows you to sort of relocate your finger on the smartwatch display, and then we're going to use the XY location of your touch-up location. We're running this with, so in 2015 we had a paper at Chi on VelociTap, and so we're using a probabilistic decoder to do the autocorrection. And so you can refer to that paper for all the details, but basically the idea is it's using a very good language model, and it's using a character language model in tandem with a word language model. And we train it on billions of words of data that's well matched to mobile data. And then we're using a very simple touch model. So the idea is each of these keys has a two-dimensional Gaussian centered over it. And then we use that Gaussian to produce a likelihood for each of the tap locations. So it's a very simple touch model. So really it's the language model that's providing a lot of the signal here. Okay? So let me show you a short video. So in this video, I'm going to be tapping, and I'll be swiping to the right whenever I want autocorrection. And I can either type a single word, which is what I'll do in the first instance. And when I swipe to the right, it will do the autocorrection. And now in this case, I'm going to type 2 words at a time. And it's going to both autocorrect and infer the spaces between the words. So this is an example of doing word at a time or 2 word at a time. So here's an example where I'm going to enter an entire sentence. And so you can see if you can try and figure out what that sentence is. Oh, okay. So anybody want to wager a guess? Oh, I had more words. All right, coming up with words is hard. Okay. So that's the idea. And so what we want to do is figure out what are sort of the human entry rate, error rate, and sort of user preferences with these different entry techniques. So we set up our first experiment. It's a within subject experimental design. We have 3 different conditions. The apparatus is exactly the same. We're using the same keyboard, same decoder algorithm. The only difference between the 3 different conditions is the instructions we gave the participants. So in the first condition, we're telling them enter 1 word and then swipe to the right. In the second condition, we say enter 2 words and then swipe to the right. And in the final condition, we say enter the entire sentence and then swipe to the right. Their task is to remember a memorable sentence. So we show them a sentence, they're told to try and remember it. And then once they hit the OK key, the sentence disappears. We show the keyboard, they enter the sentence, And then once they're finished, we show them their entry and their error rate for that sentence. And because we know which condition they're in, we also tell them, did they do the right number of recognition actions? So if they were supposed to do word at a time entry, we expect the right number of right swipe gestures. So we can give them feedback whether they're sort of obeying the instructions of the conditions. So they did 4 practice phrases, and then they did 12 phrases in the evaluation conditions. I didn't show it in the video, but they could also swipe to the left to do a backspace. So this allowed them to correct any sort of erroneous keystrokes before the recognition. So we didn't allow any recognition any correction after the recognition actually occurred. So they could only do sort of correction as they were typing their noisy input. So here are the results. So on the left we have the entry rate. And what we're seeing is kind of what you might expect. As you go to sort of these longer input sizes, we're going from sort of 26 words a minute in the word condition to 29 words a minute in the 2-word condition, and then 32 words a minute in the sentence. So they're doing less of these right swipe actions, so there's less motor actions, so they should be faster, as well as they're doing less sort of starting and stopping in their text entry. The real story, I think, in this paper is about error rate. And so in the graph in the center, we're showing the character error rate of the 3 different conditions. And while these differences weren't significant, we are seeing sort of what looks to be an upward trend in the error rates. So the error rates are all probably acceptably low for sort of casual text entry. So maybe, if you have 3 or 4% error rate, that's okay for casual messaging, or maybe entering text to Google search engine or something like that. But this is kind of concerning. Like, this is not what I was sort of expecting in this. I was hoping sentence entry would provide that probabilistic decoder with more information. We get more accurate recognition. And we're actually going to see in a follow-up offline experiment that this is really a result of sort of not having enough computational resources on the watch. And the right graph is actually showing, we started to dig into this, and so this graph is showing the literal error rate, and that's the error rate before any autocorrection. So if we basically just take the closest key to every key press, what was their error rate, getting rid of, just ignoring all the spaces. And here what we're seeing is actually they're getting more accurate. So we're going from sort of 19% literal error rate down to 15% in the sentence entry. So the human is actually being more accurate as they provide these longer input size chunks. And so we should be able to get more accurate recognition, and we'll see that in a second. A couple other things we measured. So we measured how many times they did this left swipe, the backspace, and it was kind of similar, and it didn't occur that often in any of the conditions. So really the users were trusting the autocorrection algorithm to bail them out. How often were they doing what we told them in the condition? So we measured how often they did the right number of right swipe gestures in each condition. And they were obeying pretty well in the sentence and the word conditions at 99% and 98% correct behavior. The word condition, they were doing 94%. So going 2 words at a time was not very natural, and it was kind of a compromise. It was an easy instruction to give participants, but it's probably not how you would really do it. In the real world, you'd probably segment it sort of on a more phrase level that kind of made more semantic sense. So this is sort of, this was our first experiment. So at this point, the participants have been exposed to entry at word, phrase, or sentence at a time methods. And so what we wanted to see is how would they, what would they use in practice? So if they could do anything, what would they do? So in our second experiment, we had the same 24 participants enter text in 2 different conditions, and we told them they could do word at a time, phrase at a time, or sentence at a time entry as they saw fit, and they could change it within the same condition. We wanted to know how they would use this in sort of the real world, and in the real world, we don't enter, memorable phrases, right? In the real world, we, come up with things in our head, and then we write them. And so we used a composition procedure in one of the conditions. So this is work we did in SIGCHI in 2014. And so in the compose condition, their instructions were to invent and type a fictitious message, write with good grammar and spelling, do not use abbreviation of slang, and then we just told them to swipe right after 1 or more words. And so we wanted to compare that against a more conventional text copy task. And so again, they did 12 phrases in each of the conditions. So what were the results in experiment 2? So again, we see the entry rate in words per minute on the left. And as you might expect, they're a little slower in the compose condition. So as you're composing a message, sometimes you're having to stop and maybe think of what you're writing. So it slowed them down a little bit. So they went from 33 words a minute down to 30 words a minute in the composition condition. Backspaces per character, we see there is an elevated level of that in the compose condition. So as you're composing your own novel messages, sometimes you probably, type something, you change your mind, and so you've got to backspace it a little more often. What we really wanted in this experiment was to see sort of how did their behavior change. And so the easiest sort of metric and most reliable one we could come up with is how often were they entering their compositions or their text copy tasks sentence at a time. So we measured how often that happened, and what we see is in the copy condition, they're going sentence at a time more often in the copy condition than when they were asked to compose. And again, it probably makes sense that if they're doing novel compositions, they're having to sort of periodically maybe think of what they're going to add on to their input. To kind of tease that apart a little more, we kind of wanted to know, did sort of the difference between the copy task and the composition task, did that actually impact their behavior? And so what we did is we plotted, so to sort of break this down, what we have on the x-axis is all the participants. So the same participant, this is like participant 1 on the left, and this is also participant 1. So we basically order them according to their mean entry rate. But the same participant appears in the same location on the x-axis. And what we did is we measured how many words they entered per recognition event. So people on the left end of this graph are typically just entering text 1 word at a time, or people on the right-hand side of this graph are entering things usually an entire sentence at a time. And what you can kind of make out of this graph is that people had the sort of same preference. Some people like to go word at a time, other people like to go sentence at a time, and then there were sort of some people in the middle ground that kind of maybe did phrase at a time entry. And people seem to be fairly consistent. It didn't seem to affect them which particular task they were given. So coming back to this earlier graph on error rate, so these are the same 2 graphs I showed you earlier. We've got this thing where the error rate seems to be going up as they're providing more input, yet the human is providing more accurate typing information. So what's going on here? We took the data from experiment 1, and then we moved it off the watch and we put it onto a server, and we reran the data, we ran the recognition on that noisy tap information. And so the top row in this table is showing you the error rate. So these are the same error rates. You get pretty much the same answer running it on the server. And to get it onto a watch, we really had to smash the language models. So we traded these really great language models, and then it made me kind of sad inside. I had to make them small enough to fit on a watch. And furthermore, we don't have a lot of compute power on a watch, and so VelociTap controls its speed accuracy trade-off using a search beam, and we had to use quite a narrow search beam in order to get sort of acceptable latencies on the watch. And the middle row basically shows you that if you have a bit more memory, so something like a mobile phone, and you have a little more compute power like a mobile phone, this problem you can actually leverage this better accuracy of the users to get better accuracy for the longer input sizes. And it costs you, some time, 8 times as long, but still an acceptable amount of recognition delay, okay? And you don't really need anything bigger. You use bigger models, you don't get any further gains. Final computational experiment. So we also wanted to know, it really should be the case that providing more input to a probabilistic decoder allows it to make better answers. And what we did for this was we took the word at a time data from experiment 1 and 2, so that harder data where the human was being a little more accurate. And what we're going to do is we're going to simulate people entering stuff in bigger chunks. And we're just going to splice that noisy tap data together and then run it through the VelociTap decoder and see how it affects recognition accuracy. And kind of the interesting finding is how you splice it together matters. So so the red curve here is if you tell the decoder where the separation is between the different words, you actually do get the expected accuracy gain using longer input lengths. If, however, you force the decoder to infer those spaces between words, then you don't get that accuracy gain, and it's kind of a wash. So it doesn't hurt you to provide longer input, but the fact you have to infer those spaces makes it more challenging for the recognition engine. So here are the takeaways. If you want to go faster on your phone or watch, you could type on your virtual keyboard and provide longer input. You can do this on your iPhone or your Android. Just type and then don't enter any spaces. And when you hit the spaces, it's going to autocorrect and infer the spaces. Even without any kind of correction algorithm on the recognition results, you still get pretty acceptable error rates. Users seem to have a preference. They were kind of split between doing word at a time entry or sentence at a time entry. The interesting finding we weren't expecting was sort of doing this longer input allowed the human to sort of be more accurate in their targeting of the keys. And so that's quite good. And if you have the computational resources to do a good enough search, you actually get lower error rates by doing that. And finally, kind of an implication perhaps for design is if you can allow the user to signal the spaces between words and postpone recognition, you can get a further further increase in accuracy. Okay? And so with that, I'd like to thank our sponsors and thank you for listening.
Hi, Scott McKenzie from York University. Wow, there's a lot packed into that talk. One of the things I'm wondering, and I might have missed this, but your autocorrect swipe, was it also autocomplete? Or did you have to enter?
You had to enter the entire, yeah. So we considered using, providing, sort of autocomplete word predictions,
yeah.
But we didn't in this work.
I'm amazed that you're getting 30 words a minute without any kind of prediction. That's almost unbelievable, but that's it.
Yeah, well, it's consistent. There's been now several studies on watch form factors.
Yeah.
It's
It really is amazing. Now, the question I have, the other question, nobody's behind me, so. In the first study, you had an independent variable with 3 levels. These are the word, phrase, and sentence completion. And you used a within subjects design. Now, this is one of the situations where a between subjects design is usually better because the levels of the independent variable, each one is a little bit more complex than the neighbor, if you know what I mean. And often what you get is a significant group effect if you use a within subjects design where the levels of the independent variable are sort of confounded by complexity, things like that. You didn't present any ANOVA results. I'm wondering if the group that began with the word condition, as a group, they did all 3 conditions, of course, but as a group, did they perform better than the other groups? Do you understand my question?
Is there an order of fact? I mean, we counterbalanced the conditions.
Of course, but the group that began with the word condition had an advantage, the group, because they began with an easier condition, so the learning effect would be better for them. Maybe you're not quite getting what I'm saying.
Well,
I'm wondering if there was a group effect
Yeah.
in the first user study.
We didn't specifically look at that, no.
Sorry?
Yeah, we didn't specifically, look at that, no.
Did you do an ANOVA? Because you didn't report it in. It's probably in the paper, but here it is.
I mean, it was repeated measures analysis.
Yeah, I'd be curious to know if there's a group effect. I mean, this could explain your, word, phrase, sentence thing. So you might want to have a look at that. Anyways, okay, thanks.
Hi, thanks for your talk. I was wondering what kind of language models specifically you were using. You mentioned the sizes, but were they trigram character models?
Yes. Yes. So the word model was a 4-gram word model, and the character model was a 12-gram character model.
And did you try to vary the relative position of the window relative to the position being predicted? So when you have a sentence length input, you could look at 3 on the right, 3 on the left, or 6 behind you.
I mean, so we're always going sort of left to right, right? So you're,
Left to right, okay.
I mean, so you're talking about sort of using the right context is what you're, I mean,
Well-
we're always using as much context as we had. So as you went word at a time or two words at a time, we used whatever the recognition of the left context was in,
Yeah.
you know, the subsequent recognition events.
I see, thank you.
Yeah.
Super quick, Matt. So you pair, can you go back to the last slide?
Yeah.
So you, you paired a swipe to the right as space plus recognize me, please. With hindsight, what do you think about shifting your keyboard up a little bit and putting a space bar in there, and that being an ambiguous, an error-prone space bar?
Yeah. Yeah, so using a sort of a, I mean, are you suggesting a probabilistic spacebar or
Yeah.
deterministic? Yeah, certainly, I mean, we could do that, yeah. And I mean, we really did have the real estate in this case. We could have that, or perhaps another design I kind of like is sort of using this upper area. So this area is sort of a big virtual spacebar. You know, so that's a very big target that wouldn't even need to be probabilistic. Because one of the disadvantages of the swipe gesture, it was fairly sort of time consuming to make that right swipe gesture. And so a tap is a lot faster.
Fantastic. If you could thank all our speakers from our session.